Let's go over this modeling activity using trig functions. So here we go. Whoa. Given the plane's height h is 3,200 feet, what is the distance d to the nearest foot from the plane to the control tower? And I'm guessing that this is the control tower, not a golf tee. All right, so let's look into this. We can mark the diagram with the information we know. We know the height is 3,200 feet. That's great. We know that we're looking for the distance, which is right here. And we know this angle is 36 degrees, and that information was exclusively given to us in the diagram. So what we can do now is, now that we know the identified angle, and we can now start labeling the diagram. So this will be the opposite side. This is the hypotenuse, and this is the adjacent side. So what do we pick? What trig function are we going to pick? We know the adjacent. We're looking for the hypotenuse. So which trig function has adjacent and hypotenuse in it? Cosine. So I'm going to make my trig function now. Cosine of 36 degrees equals the adjacent, which is 3,200, over the hypotenuse, which is d. Now, our variable is in the denominator, so multiplying d by both sides isn't really going to help us out. Actually, it would work just fine, but we'd have to do it in two steps. So we're going to use that property of proportions, and we're going to swap the location of cosine 36 and the d to isolate the variable. D equals 3,200 divided by the cosine of 36 degrees. And we can just throw this whole thing into the calculator. Make sure your calculator's on degrees. And here you go. And I got 3,955.417528. And it says, what is the distance to the nearest foot from the plane to the control tower? So we're going to round off all the decimals, and it's 3955.4. So we will call it 3955, and it's feet. Here units are actually important, so you should always add those in whenever appropriate. Moving on to number 2. An 82-foot, 8-inch long wire is attached to the top of a telephone pole, 41 feet, 4 inches tall. What is the exact measure of the angle the wire makes with the ground? So we're looking for an angle. And we have some information here. The wire is 82 feet, 8 inches. And the telephone pole is 41 feet, 4 inches. And these feet and inches make this a much more difficult problem. What is the exact measure of the angle the wire makes with the ground? So the angle between the wire and the ground is going to be down here. That's where theta is going to be. And that's what we're going to solve for. So we know what angle we're looking for. Let's mark our diagram. It's the opposite. This is the hypotenuse. And this is the adjacent. So I know the opposite and the hypotenuse. I'm going to use those two. But they're in this feet and inches measurement. So I believe I'm going to switch to decimals for this. 4 inches, it would be like 4 over 12, which is 1/3. So it would be like 41.3 repeating, and then it would be 8 over 12, which is 2/3. I don't know if I want to do decimals. All right, I have a better idea. Let's do it. Let's just convert these into inches. Now there's going to be a lot of inches, but then we won't have to worry about the difference between feet and inches. And when we solve it, our answer is going to be in degrees anyways. So whether it's feet or inches doesn't really matter. So 41 feet, 41 times 12, is 492 inches. Add to that the 4 inches, and you get 496. So I'm going to call this 496 inches. Now 82 feet, 82 times 12 is 984 inches. And I'm going to add to that the 8 inches, and I get 992 inches. Okay, so now at least we have a consistent measurement that we can compare. So I can start building my trig function. We know the opposite in the hypotenuse, so that's sine of theta will equal, the opposite of the theta is 496. Oh, I wrote that wrong. .496, and the hypotenuse is 992. So the fact that those are large inch numbers isn't going to really affect us. All we want to do now is move the word sine over to the other side, and when we do that it becomes arc sine. So theta equals arc sine of 496 over 992, and I can do that in my calculator. Arc sine of 496 divided by 992, and I get 30 degrees. And does it say what it is? What is the exact measure? Well, it is exactly 30 degrees. It's not a decimal. It's really 30 degrees. So I'm actually going to erase my approximately with an equal sign. And theta equals 30 degrees. Excellent. Let's move on. A 10-foot long ladder reaches a point 5 times the square root of 2 feet high on a house. Okay. I'm going to use something that will be obvious. 5 times the square root of 2. What angle does the ladder form with the ground? Oh, and the ladder itself was 10 feet. And what angle does it form with the ground? Okay, I know a lot about special right triangles, and I know what this answer is going to be right now, but I'm going to show you how you can use trig to find it and get exactly the same answer. So, the angle that we care about, our theta, is there. This is the opposite. This is the hypotenuse. And down here would be the adjacent. Okay, so now we got to pick our trig function, sine, TOA. We're looking for theta. We know the opposite and the hypotenuse. So we're back to sine. Sine of theta will equal 5 times the square root of 2 over 10. And then we move the word sine over to the other side. Theta will equal arc sine of 5 times the square root of 2 over 10. And arc sine of 5 square root of 2 over 10 equals 45. And it equals 45 exactly. Now, I don't recommend anybody get on a ladder that is at a 45-degree angle. Doesn't seem like it's the right angle. However, that's what it is making. The bottom of this, since it's a 45-degree angle, will also be 5 times the square root of 2. This is a 45, 45, 90 triangle. And even if you couldn't remember that with special right triangles, if you knew the trig, you'd be able to do it. And later, when we talk about the unit circle, you'd actually be able to do that without a calculator. At 20 meters long, a 20 meters long line reaches a point 10 times the square root of 3 meters high on a ship's mast. Okay, so What angle does the line form with the mass? Okay, so the mass is on this side. This is the angle we're looking for. And this is 20 meters long. And this is 10 times the square root of 3. And this is a special right triangle as well. This makes a right angle, hopefully. And the 20 meters is the hypotenuse. The middle length side is 10 times the square root of 3. And the small side is going to be just 10. This is a 30, 60, 90 triangle. And the angle that we're looking at there is opposite the middle length side, so it's going to be the middle length angle. And so our theta in this problem will equal exactly 60 degrees. You could have also done it with trig. I'd use sine. It would be sine of theta is 10 times the square root of 3 over 20. And then if you take the arc sine of 10 square root of 3 over 20, you would also get 60 degrees. Number 5. A mountain road rises 5 meters for every 30 meters of road. It's very interesting because I've noticed in a lot of shops this is how they give slopes. They go, it raises 4 inches for every foot or something like that. And so I'm glad they asked the question this way. So a mountain road rises 5 meters for every 30 meters of road. What is the measure of the angle of incline with the horizontal? Round your answer to the nearest tenth of a degree. Now, the overall distance won't matter in this because we only care about a section that will go up 5 meters for 30 meters of road. So the road is going uphill, and it raises up 5 meters for a length of 30 meters. And we are looking for the angle of incline with the horizontal. So this will be the angle of incline with the horizontal, because the horizontal line would be like the base. How much angle of that goes up? Our theta will be over here. We could label the diagram. This is the opposite over the hypotenuse. A lot of sine going on here. And this is the adjacent. Don't care about the adjacent and one. We only care about opposite and hypotenuse. So that's sine. Sine is opposite over hypotenuse. Sine theta equals 5 over 30. You can reduce this if you want. That would be 1 over 6. And then move the word sine over to the other side. So theta equals arc sine of 1/6. I can figure that out on the calculator. Arc sine 1 over 6. 9.594. And it says round your answer to the nearest tenth of a degree, so 9.6. And we're back to approximately here. It's 9.6. And that's our answer. Yay! Here we have a question apparently from Texas. A wire is attached to the top of a 6.5 meter tall flagpole. So this is 6.5 meters and forms a 30-degree angle with the ground. So the wire is attached to the top to a 6.5 meter flagpole and forms a 30-degree angle with the ground. How long is the wire? So this diagram is horrible because if it forms a 30-degree angle with the ground, this angle down there that I marked is 30 degrees. Even though it looks much more like 60 degrees. It's really 30 degrees because it's forming it with the ground, not the flagpole. If it was a 6.5 meter tall flagpole in the wire, what angle is the wire form with the flagpole? That would make more sense in this diagram. But in this case, we're looking for the length of the wire. So that's over here. We'll call it X. That looks like a deranged plus sign. I can do better. X, not much better. And we know an angle. Let's label our diagram. This is the opposite. This is the hypotenuse. This is the adjacent. And you got to really kind of put this out of your mind because this wire is going to be pretty long compared to the flagpole height. So we have opposite. We're looking for a hypotenuse. And again, we're going to go with sine, opposite and hypotenuse. We don't care about the adjacent. So sine of 30 equals 6.5 over x. Now, I know I can solve this with special area triangles, but because the diagram looks so weird, I think it actually might be easier to do using trig. So x equals 6.5 over the sine of 30. Just flipping the denominator with the numerator of the other side. 6.5 divided by sine 30. And I get a very even number, 13. And since the only measurement we have in here that has a length is meters, it's 13 meters. Which is just 6.5 times 2 if you were doing special area triangles. All right, moving on to number 7. We're on to 7. A 1.3 meter long ramp makes an angle of 29 degrees with the ground. All right, so this diagram looks a lot better already. That's 29 degrees. Approximately how far above the ground is the back end of the ramp where it meets the truck? So I forgot to write it, but this is 1.3 meters. And so we're going to make this into a triangle, a right triangle, and we're going to solve for x here. So we have 29 degrees, we have x, which is the opposite, and we have 1.3, which is the hypotenuse. Still no adjacent. And we can set up our trig function. It's opposite and hypotenuse. Again, we've done this a bunch of times. It's going to be sine. And now our variable's in the numerator, so I can move the 1.3 over to the other side by just multiplying it. It'll be 1.3 times the sine of 29. That equals x. And my answer for x equals, what does it say? Round your answer to the nearest tenth. It's 0.63025. So 0.63, so I'm going to round that to 0.6 meters. And it is approximately, so I'm going to change that to an approximation. And that's okay. It could be, 0.6 meters tall. It's only 1.3 meters long. It kind of makes sense in the scheme of our problem, even though it's a decimal answer. And a lot of the times these at least have one unitary whole number digit. 8. A tower is supported by a guy wire. Oh, no diagram. Build your own here. Tower supported by a guy wire, which is a wire that goes like from the ground to the top of the tower at an angle. 10 meters in length. The guy wire meets the ground at an angle of 50 degrees. To the nearest meter, at what height on the tower is the guy wire attached? All right. So we have a tower. I don't know what the tower is going to look like. Let's just put it like this. And maybe a couple things hang down from it, and it's like running wires. Say it's that kind of tower, like an electric tower. And then there's a guy wire 10 meters in length making a 50-degree angle to the wire. So to me, let's change, not that one. Let's change colors to this, and we get a wire that goes up at some point on this, and that is 10 meters tall. And we can make this into a makeshift right triangle. The guy wire meets the ground at an angle of 50 degrees. This will be 50 degrees. So we have a height Oh, the guy wire is 10 meters in length. That means that I put the 10 in the wrong spot. The 10 should be over here, 10 meters. And what we're looking for, our x is this side, the opposite side of the 50 degrees. Oh, we shouldn't label this. That's the opposite side. That's the hypotenuse. Apparently this whole thing is all sine. That's the adjacent side. We don't know, we don't care about the adjacent side. The wire itself is 10 meters long. And we're trying to see how high up on this tower it is placed. So we know the hypotenuse, we're looking for the opposite. We're going to use sine. Sine of 50 equals opposite x over hypotenuse 10. We have the 10 in the denominator, so multiply that by both sides. So you get 10 times the sine of 50. Whenever we multiply like a number by like sine 50, you always put it in front because it makes it easier to read. And also then you don't have to worry about the calculator thinking you're taking the sine of like 5010. That would be weird. And that equals x. And in multiplication, it doesn't matter if you multiply what order you multiply in. It's the commutative property. So we put it in front, so it just makes it easier all around. 10 times the sine of 50 on my calculator is 7.66. So x is approximately to the nearest meter. So 7.66 meters is approximately 8 meters. Excellent. Mont Blanc, which is the French way to say Mont Blanc, is the highest of the Alps. It is 4.8 kilometers high. Wow. The angles of elevation from the points A and B are 43 degrees and 54 degrees as shown. Great. Calculate the length of the tunnel AB. Ooh, we're going to have to do this problem twice. To the nearest tenth of a kilometer. Okay, so we're going to have to figure out from A all the way to B, all the way across. And we're going to do that by first finding out what AD is. So we're first going to find out what this side right here is. I'll put 2 lines in. And then we're going to find out what this side right here is. And then once we find those two values, we're going to add them together, and that's going to be the entire distance A to B. A little segment addition postulate here. So let's find AD first. So I'm not going to do this normal stuff. 4.8 is always going to be the opposite. It's opposite the 43 degrees in one triangle. It's opposite the 54 degrees in the other triangle. And we're always looking for the adjacent. So finally, we're not using sine. We have, I guess I'll write it. So, toa. This is going to be the opposite side, and this is the adjacent side. And I'll just write over here too. This is also the adjacent side. It's adjacent to the 54 degrees. The hypotenuses are up here, and they're not going to factor in to this problem at all. So we're going to use opposite and adjacent both times, and so we're going to use tangent. So the tangent, let's find AD first. The tangent of 43 degrees equals opposite over adjacent. The opposite is 4.8, and our answer is in kilometers. So that's very good. That makes this a lot easier. 4.8 kilometers over, and then at the bottom I'm just going to put AD, because that's, the distance from A to D when you write two variables like that. Okay, for this one we swap their locations. AD will equal 4.8 kilometers divided by the tangent of 43. 4.8 divided by the tangent. Oh, I'm going to write this fraction. 4.3 over the tangent of 43. Now here's kind of a tough part. We want the answer to be the nearest tenth of a kilometer, but I'm going to round it a little bit beyond that. I'm going to round it to 3 decimal places just to make sure. Actually, we're just adding the 2 at the end, so I can round it to the nearest tenth. We have 4.6111. So I'm going to round that to AD is approximately 4.6. And since we're not multiplying the answers at the end, we're just adding them, we can round in each step. But if we were multiplying or dividing, we'd need to add extra digits on in our intermediate steps to have it accurate to the nearest tenth for our final answer. Okay, now it's time to find dB. So I'm going to write another trig function, tangent 43. Oh, nope, this time it's 54 equals 4.8, the same, opposite side, over dB. So we're going to swap the dB and the tangent 45 again. So dB equals 4.8 kilometers divided by tan 54. And I got 3.487. And once again, we're just rounding. We're just adding these two results together. So if I round this correctly to the nearest tenth, and I add it to another thing rounded correctly to the nearest tenth, I should get the correct answer. So this will be 3.48 rounds to 3.5 kilometers. Okay, so I have a 4.6 and I have a 3.5. So I can add those together. And I get 8.1 kilometers. Now to double check, I used the stored values on my calculator, and so instead of 4.6, I use 4.611185453, and instead of 3.5, I use 3.48740. So I use like more decimals, and I add them together, and I got 8.09, which will also round to 8.1. So our answer is correct, even though we used the shorter ones, the shorter estimations. Swimming pool is 40 feet long, great, and 3 feet deep at one end. If it is 10 feet deep at the bottom of the other end, find the total distance along the bottom. Whoa. Okay, so the pool, I think this is like the bottom of the pool. Let me see if I can do this. This is the bottom of the pool, and it kind of goes down at this angle. And then this dashed line shows like the difference, but this is a bigger difference than they're showing. At this side right here, it would just be 3. And at this side right here, it would be 10. So the angle of depression is going to be kind of weird on this one. So this is 3 feet. This whole thing is 10 feet from the surface of the water, which is up at the top, to the bottom would be 10 feet, and it's 40 feet long. So this isn't the greatest, the most accurate diagram. I think that angle is going to go a lot further, because this line right here is 3 feet. And that means that this bottom part below it has to be 7 feet. And it certainly does not appear that it's 7 feet in the diagram. But what we really care about in this diagram, change my color here, is this triangle right here. Because from this triangle, we have a right angle, and we know that this length is 40 at the top, and we know that the base of it, this side, is 7. And so we can figure out what the total distance along the bottom. Oh, we don't even have to use trig for this. We know one's 40, one's 7. This makes a right angle over here. And so we can just use the Pythagorean theorem. This is the hypotenuse. We don't know the angle. We don't need to know the angle. We have one side which is 40, one side which is 7, and then the hypotenuse. So I can do a squared plus b squared equals c squared. The hypotenuse always has to be c squared. The other two sides don't matter. I usually make the smaller one first. 7 squared plus 40 squared. Alright, and 7 squared plus 40 squared. Oh, I'm going to fix my calculator. 7 squared is 49, and 40 squared is 1600. Add those together, you get 1649. That's what c squared is. We have to take the square root. So the square root of 1649 is 40.60. And it says find the total distance along the bottom. And that just doesn't seem like a lot, but it's probably right. So it's 40.6 feet. I think everybody would get tripped up with this part right here, the fact that this is 3 feet and this is 7 feet. Because the diagram doesn't really indicate that. And then the answer is bizarrely small, because 40 feet long is way longer than the 3 feet height that they identified. Like, this looks like, if this is 40 feet, this looks like it's about 12 feet, but I don't know. That's our answer. 40.6 feet. A little Christmas in there. All right. So thank you for listening this far, and good luck.